Binary search. If there's one algorithm interviewers expect you to speak fluently, it's binary search. It's the litmus test for algorithmic rigor, pointer discipline, off-by-one control, and logarithmic thinking. This pattern mastery 100 staple shows up everywhere, from search problems to boundaries and monotonic checks. Let's lock it in using basics so your explanation and code are crisp and unbeatable. We're given a sorted array nums and an integer target. Return the index of target if found, otherwise return -1. Because the data is sorted, we can eliminate half the search space each step by comparing the middle element to the target. Binary search runs in O log n time and O1 space, way better than a linear scan. Key pitfalls: computing mid, updating left and right correctly, and using while left less than equals right to avoid infinite loops. We'll return as soon as nums mid equals target, else move the appropriate boundary. Plan: initialize left equals 0, right equals len nums -1. While left less than equals right, compute mid. If nums mid equals target, return mid. If it's smaller, discard the left half by doing left equals mid +1, otherwise discard the right half via right equals mid -1. If we exit the loop, return -1. Let's try to implement it using solution 1. We're defining a function called search that takes a sorted array nums and a value target. We set two pointers, L at the start of the array, and R at the end of the array. Now we run a loop while L is less than or equal to R, because we're narrowing the search space. Inside the loop, we calculate mid as the floor of L plus R, 2, which gives us the middle index. If nums mid equals target, we found it, so we return mid. If nums mid is less than target, that means the target must be on the right side, so we move L to mid +1. Otherwise, nums mid is greater than target, so the target must be on the left side, and we move R to mid 1. If the loop ends, it means the target is not in the array, so we return -1. Time complexity is O log n, because we cut the search range in half each step. Space complexity is O1 because we only use a few variables. Let's verify solution 1 for binary search. Input is nums equals -1, 0, 3, 5, 9, 12, and target equals 9. We start with L equals 0 and R equals 5. Mid is floor of 0 plus 5 over 2, which is 2. Nums 2 is 3, which is less than 9, so we move L to 3. Now L is 3 and R is 5. Mid is floor of 3 plus 5 over 2, which is 4. Nums 4 is 9, which matches the target, so we return 4. The output is 4, and the expected is 4. They match, so solution 1 is correct for this test case. Now let's try to implement it using solution 2. We're defining a function called search that takes a sorted array nums and a value target. Inside it, we define a helper function called helper. It takes two pointers, L and R, representing the current search range. In the helper, the first check is the base case. If L is greater than R, it means the range is empty, so the target is not found, and we return -1. Next, we compute mid as the floor of L plus R over 2. If nums mid equals target, we found the target, so we return mid. If nums mid is less than target, the target must be in the right half, so we recursively call helper mid +1, R. Otherwise, nums mid is greater than target, so the target must be in the left half, and we recursively call helper L mid -1. Finally, the main function starts the recursion by calling helper 0, nums.length -1, and returns whatever the helper returns. Time complexity is O of log n, because we cut the range in half each call. Space complexity is O of log n, because recursion uses the call stack. Let's verify solution 2 for binary search. Input is nums equals -1, 0, 3, 5, 9, 12, and target equals 2. We start with helper 0, 5. Mid is floor of 0 plus 5 over 2, which is 2. Nums 2 is 3, which is greater than 2. So we search left by calling helper 0, 1. Now L is 0, and R is 1. Mid is floor of 0 plus 1 over 2, which is 0. Num 0 is -1, which is less than 2. So we search right by calling helper 1, 1. Now L is 1, and R is 1. Mid is floor of 1 plus 1 over 2, which is 1. Nums 1 is 0, which is less than 2. So we search right by calling helper 2, 1. Now L is 2, and R is 1. So L is greater than R. That means the range is empty. So we return -1. The output is -1, and the expected is -1. They match, so solution 2 is correct for this test case. Let's wrap up binary search. This is one of the most important fundamentals because it teaches you how to search efficiently and control boundaries with precision. Binary search finds a target in a sorted list by repeatedly checking the middle and eliminating half of the remaining range. Instead of moving one step at a time, it uses order to make bigger decisions, cutting the search space in half on every iteration. We compared it against a linear scan and saw the advantage immediately. Linear search is O(n), while binary search is O log n. The real difficulty isn't the concept, it's correctly managing pointers, computing the midpoint safely, and ensuring the loop or recursion terminates without getting stuck. The structure is consistent. Start with left and right pointers, compute the midpoint, and compare the middle value to the target. If the target is larger, shift the left boundary rightward. If it's smaller, shift the right boundary leftward. You keep narrowing the window until you either find the target or the range closes. We implemented the approach successfully on LeetCode without errors using a clean loop that halves the search range each step. The pointers guided the narrowing process, and returning the midpoint as soon as it matched kept the solution minimal and robust. We verified behavior across multiple LeetCode test cases, returning the correct index when the target exists and returning -1 when it doesn't. Those results confirmed the logic was correct and consistently achieved logarithmic performance. The takeaway is that binary search is a mindset, not just a tool. It trains you to reason in halves, maintain strict boundaries, and make efficient decisions, skills that show up across many interview problems well beyond searching.